That was quite a set of heuristics and ad hoc things. Looks at least like that. Well, the basic intuition of Proclos is that we have k-medoid. Okay, k-medoid is about, we have a set of candidate medoids and we try to exchange current medoids with not yet current medoids in order to increase the cluster quality. Yeah? The compactness of clusters typically. Well, so far so good. Now we incorporate the subspace learning, and the only thing that we do is, well, in each step we look at the locality of each cluster medoid and basically make something like a variance analysis. Yeah. So what are the features that have a small variance, and what are the features where the spread is high? And we focus on those where the spread is small. Yeah, because those are the features that are probably relevant, meaning that the locality, the points in the locality of this medoid are packed very, very, very strong together. Yeah, so that is the basic idea. And in each iteration of the algorithm, we look at this entire dimensionality locality and the locality of medoids according to the entire dimensionality, and look which are the features that are close together. And which are the features which have a high spread among the points in the locality. And we look only for those, or we want to extract those that have a small variation. Yeah? And the heuristics is that we come up with k times L on average. Yeah? So that on average each cluster each cluster representative gets L relevant features. Yeah? Can be more, can be less, of course. So that is the basic idea of Proclos. Now, let's see if we can do, let's see if we can do it a little bit different. Well, we can do it, of course, a little bit different. We could use, instead of k-medoid, maybe also, again, density-based clustering approaches. I mean, we had mostly density-based clustering approaches in subspace clustering. And we can also use density-based clustering algorithms, or the density-based clustering model, for this top-down subspace search. And we do that now with the so-called predecon algorithm, which takes the dbScan clustering algorithm. Yeah? So instead of k-medoid clustering, we take dbScan. And in dbScan here, we use a special distance function that somehow models or represents the subspace preference of points. Yeah? Recall that dbScan, we look for core points. And then if we have a core point, we try to find those transitive chains of, well, a core point finds the core points among its neighbors, finds the core points among its neighbors, finds the core points among its neighbors, and so on and so on. And then if we follow all those chains, we find the entire cluster. And we do the same now here. So we use dbScan with a distance, but with a distance function now that adopts the subspace preference, meaning that we look for those chains, but we want to look in those directions that somehow reflects the subspace preference. Yeah? And since we look for neighbors of points, or neighborhoods of core points, those neighborhoods should be somehow squeezed so that they represent the subspace preference. Yeah? So we don't want to look for full dimensional spheres, but we want to look for spheres only in those features that are relevant to each other, to our feature, to our cluster. Yeah. So how can we do that? Well, we can introduce a weighting scheme for our distance function. Yeah, and the weighting scheme is quite easy. And the weighting scheme is per point. Yeah, and it reflects the subspace preference of a specific point. Meaning, what are the features of the point, what are the features such that if we consider only those features, the point somehow clusters best, whatever that somehow means. Well, we see what that means. So given an input parameter delta and kappa for each point, the d-dimensional subspace preference vector, WP of P, so the subspace preference is associated with a point, and we define it as follows. We give it a 1 if the variance along the corresponding feature, well, so it's a d-dimensional subspace preference vector. So for each feature, original feature of the D features, we record one specific preference. And the preference is either 1 or kappa. 1 if the variance is greater than delta, meaning that we have a high variance, it's probably not so relevant. And kappa, which is much greater than 1, if the variance is smaller than delta. Yeah? So we look for those directions that have a variance greater or smaller than delta. So delta is the threshold deciding about not so relevant features. Those are the guys that are weighted by 1. And those features that are considered to be relevant, they are rated or weighted by kappa. Yeah? So the variance here used to decide with this threshold delta here is the variance along the corresponding subspace. Now, we can use this weight here, this weighting vector, to define a distance function, a weighted distance function. So we just use this weighting vector here in the Euclidean distance function. The only problem is that this distance function actually is not symmetric, because the weighting vector is specific to a point, right? Yeah. So we look at the points here, and we look actually in the I should have said that we look into the epsilon neighborhood of points in order to and analyze the variance of the epsilon neighbors of points. Yeah. So and epsilon is the classical dB scan parameter. Yeah. So we look in the epsilon neighborhood of the point in the entire feature space, which means that we look into the d-dimensional sphere around P with radius epsilon, and then we look to all the points in this sphere and see if they form a specific subspace preference. So in this visualization here, the points in the neighborhood reveal a specific subspace preference because they have a very small variance along AJ. So AJ would probably be rated by kappa, and they have a large preference along AI. So AI would probably be weighted as 1. Yeah? So the subspace preference vector of P will have 1 in feature AI and a kappa in feature AJ. And we do that for any point. Yeah? So each point of the data space, each observation, each data object gets its own subspace preference vector. No? Somehow reflecting the preference of the points in the epsilon neighborhood around this point. No?